Well, hello, geometry. Welcome to another week, week 17. It continues to go by faster and faster. And so, today we are discussing the last transformation. We've discussed rotations, reflections, and translations, and we talked about how all those were rigid transformations. Rigid because the shape did not change. Here, our last transformation actually changes something about the shape. Not the shape itself, but its size. And so when we talk about a dilation, think about the last time you've been to the eye doctor. They say that they're going to dilate your eyes. That is the exact same word, because what they're doing when they dilate your eyes is they're changing the size of your pupil, not the shape, but they're changing the size of your pupil, specifically making it larger. But a dilation works for making things larger or smaller. A dilation is all about keeping something the same shape, but changing its size. And so, a dilation is a transformation that changes a shape's size. And so, the thing that I guess I'm going to remind you guys, in case you didn't already know, is that an enlargement is to increase its size, or bigger. And then a reduction is to decrease its size, otherwise to make it smaller. So, those are some of the basics about the definition of a dilation. Now, we're going to talk about how much to change its shape. And when we talk about how much we change a size, we're talking about a multiplicative factor. That's why colloquially we talk about things being twice as big or 3 times as big. And so that multiplication for how much bigger a shape gets is called the scale factor. And so the scale factor is how much bigger or smaller a shape is. And so it could be 2 times as big, or 3 times as big, as 4 times as big, or it could be half as big, or a third as big, or even some weird fractions like 3/4 of as big. Now, the actual difference between our image and our pre-image, because we're still using those vocabulary words as well, right? Actually, is there a spot to include that or further up? Now I'll go ahead and write it down here. Image and pre-image, just as a reminder, is the shape after and before. The pre-image is the original shape, and the image in this particular lesson is our dilated shape, the shape after the change in size. And so the comparison between the image and the pre-image is our ratio. So ratio is just another word about comparing two things. Our scale factor is specifically the number of how much bigger or smaller it is. The ratio functionally is the exact same thing. It is how much bigger or smaller when we compare the two shapes. And so actually, I'm going to write scale factor down there. The ratio is the scale factor. And so the last word that I want to be able to tie into this is proportional. Last week we talked about a proportion, comparing two sets of fractions and solving. That was on purpose because a proportion is all about matching and comparing two things as well. So the scale factor is the number that's our multiplier, how much bigger or smaller that is. That is our ratio. Our ratio can be 2 times as big or 3 times as big or as half as big. And then the proportion is a ratio. So when we talk about all three of these words, even though we might use them in slightly different contexts, they actually all three mean the same thing. The scale factor is the ratio, which is a proportion. They're all functionally the exact same thing. So when we use a fraction to solve, we're using the scale factor to solve it. When we create a proportional relationship, we're using our ratios, which are our scale factors, to do it. All three of those words are interchangeable. And so let's actually look at an example of a scale factor here. And so looking at the example of our scale factors, let's say we have a triangle, ABC. And so I'm going to go ahead and do 2, 3, and 4. Now, if we compare that to A prime, B prime, C prime, and this is not drawn to scale, so, you know, there we go. And I make all the sides 6, 9, and 12, then the question is, what's the scale factor? What's the ratio between the two shapes? Well, you could probably guess just by matching up the points and matching up the sides, which are corresponding points and sides, that we are getting 3 times bigger. So our ratio is equal to 3. Our ratio is our scale factor. Our scale factor is 3 times bigger. Our ratio is 3 times bigger. We can check that by comparing our corresponding sides, right? 2 corresponds to 6 because they match. And so as we look at making our proportions, we're going to want to make sure we're matching the right sides and angles, matching the corresponding sides. And so corresponding means to match. And we had our original shape and the shape after the dilation. That is the pre-image and the image. And so let's just make some fractions out of this to make sure we understand what we're talking about. So for 3 and 9, 2 and 6, just picking those sets of corresponding sides. You could have picked any set of corresponding sides, but I chose those two. We can write our fractions to emphasize what our actual ratios are. Ladies and gentlemen, if you want your scale factor, then you need to have the image over the pre-image. So for your scale factor, it is your image over your pre-image as a fraction. Meaning, in this particular example, using the green sides that I highlighted first, it is 6 over 2. But ladies and gentlemen, you didn't have to use those sides. You could use any pair of corresponding sides, meaning you could use the 9 and 3 as well. As long as the image is over the pre-image, you're in great shape. So you can go 9 over 3 as well. And as you already know, whether you take 6 divided by 2 or you take 9 divided by 3, you get the scale factor of 3. So functionally, the scale factor is the ratio which is a proportion, because that's what we set up here. We set up a proportional equation. 6 over 2 equals 9 over 3. Both of those equal to 3, which is our scale factor, which is also our ratio. Ladies and gentlemen, could you have put the 3 and the 2 on top? Sure. But the thing I need to remind you is that if you do that, while these fractions are still equal to one another, while these are equal to one another, that is no longer your scale factor. So let me clarify. If you put 2 over 6 and set that equal to 3 over 9, while that's a true statement, while both of those are equal to 1/3, because you didn't put the pre-image over the image, you're not looking at your ratio. You're not looking at your scale factor. So while you can solve or do anything else that you need with that fractions, it is not your scale factor because the image is not on top. So let's take a look at one more example here, and then I'll end the video and pick up in a second video some more examples of finding missing sides using scale factors. And so, one more example here. In this example, we'll continue talking about scale factors. We'll have a nice big rectangle here. And then I'm going to name this rectangle KEWL. And I'm only going to give us one side here, which is 8. And then I'm going to look at another one that's a little bit smaller, K prime, E prime, W prime, L prime, and name the side 2. Ladies and gentlemen, based on how our points are identified with our primes, we know which one's the image and which one's the pre-image. The 2, even though it's smaller, is our image. It comes after the dilation. 8 is the pre-image. And so when we go to write ourselves our fraction in order to find our scale factor, which is represented by the variable r for ratio, then we know that the image is 2, the pre-image is 8, and so our true ratio is 1/4. Our true ratio is 1/4. So let me take this example and let's find a missing side using proportions. Ladies and gentlemen, let's go ahead and say we know what EW is. Let's pick our favorite number. Let's say EW. Since this is a rectangle, it doesn't have to be the exact same thing. 16. Why not? 16 is a great number. Let's write out a proportion to solve for EW, which I'll label as X. We want to match up the corresponding sides, image over pre-image. And so we already have the 8 and the 2. And we already figured out that 1/4 is our scale factor. But in order to solve for our missing side, we want to take the 2 over the 8 and write that as a fraction here. So to solve for X, we want to take 2 over 8 and set that equal to the image over the pre-image for the other pair of sides, X over 16. And now, like we did last week, we can solve for X. In this case, we just need to multiply by 16 on both sides. So multiply by 16, multiply by 16, and you can perform some calculator geniusry and multiply 16 by 2 and divide by 8. Regardless of how you do those calculations, you end up with X equal to 4, which is the length of our missing side here. So in this example, I tied in a few things. One, I wanted to illustrate image over pre-image to get a fraction as our ratio. Then I took that an extra step further and I said, well, what if we had a side and we were missing another one? Then we could set up a proportion matching our corresponding sides and solve for X like we did last week. So, ladies and gentlemen, we're going to continue this work in our next video, specifically looking and talking about how to find and work with dilations on a coordinate grid. Thank you guys. See you soon.